All right, 2-2. Some more graphs and displays basically, and then once we finish chapter 2 is when we're really going to start getting into some more calculations. You may have heard terms like standard deviation and mean and all those things. Then we're really going to start getting into things here. But a stem and leaf plot, very simply, it's a way of displaying the quantitative data. Remember, quantitative means there's a quantity, right? Which separates each number into a stem, the leftmost digit or digits, and a leaf, the rightmost digit. Okay? So that's the key there, that the stem can be more than one digit, and then they want the leaf actually to just be one digit. It's kind of how they describe how they want that. Again, in this class, I'm never going to ask you to verbatim put down a definition, so obviously paraphrasing is fine, because I want you to write down what's going to mean something to you. I wouldn't necessarily call it a graph. Like, that's why they didn't use that word. It's more like in a display. It does order the numbers quite nicely for you, though. Again, the leaf being just the rightmost digit is probably the most important. Okay. Everybody had a chance to get that down, at least something close to that? Good. Yeah, that was kind of a long one. So let's go. All right, so here's some numbers of Little League, or league leading, excuse me, not Little League. League leading runs batted in, which is RBIs, for those of you that are not good with the lingo of baseball there. For the American League for the last 50 years, display the data. Would you think those numbers to be relatively close to each other? So for the last 50 years, it's the league leading, runs batted in. Do any really kind of stick out at you? Yeah, 78. Any ideas where that would have come from? There you go. When they had the strike, they didn't have as many games, and so that was the league leader, 78. Okay, does that kind of throw off the data a little bit? Yeah, but there is a reason that that one's kind of in there. And so basically, what we're going to want to do here is, obviously this left part, I put that on there for you, didn't I? No, I didn't. All right, so put one of these in. So here's the stem over here and the leaf. So basically, I like to kind of find the smallest, and obviously we found that, right, 78, and then kind of find the biggest. And that seems to be very similar to what we've been doing. And that's where, again, Excel is really nice. You can just put them in order. It takes longer to enter the numbers than it does to organize them, right? 159, is that the biggest? Anybody find anything bigger than that? No? So if that's our deal, 78, you basically have to put this way. You know the 8 has to go here, and then the 7 has to go there, right? And it is a good idea. Are there any 80s? No, but it's still a good idea to put those in there so that all of a sudden your graph doesn't like jump from 70s to hundreds. All right, there are no 80s. There are no 90s, right? Are there? Nope. Are there any that are like 100 and... Okay, there is some. Okay, so that would be a 10 here. So is there any more? Let's maybe do those in red. So is there any 10 something? So let's go along at 105. 109, 109 again, 108. Did I miss one? Oh, yep, right by the other one. Okay, so what you want to do is kind of do it that way because you want to go kind of from smallest to biggest. So we know we have, what's the smallest? 105, and then, so we did that one. 108. And what do you remember from other times you've done this? I think you've done it in middle school, right? You did at least once or twice. 109 is in there 3 times. You just write the 9 3 times, exactly. Okay, you get the idea. And so then you can cross all of those off. It's always a good idea to kind of try and stay organized in some way. Okay. And at this point, I think you understand the stem and leaf, so you can finish that one if you want. Or what we'll do is I'll just put the answer up here, and you can always look in the recordings if you want to just, you know what I mean? Then you can just look in the recordings and write it down if you want. I think you get the idea, right? It'd be kind of overkill to have you necessarily write all those down. So that's completely up to you. If you want to write them all down, go ahead. I'm not too concerned about it. We can just look at it and talk about it if you want. Up to you. So again, that 78 really sticks out now, right? It might not have at first, but it really sticks out And what also sticks out is those, the 155, 159, that's on the other end. But do you agree a majority of the data is 1-teens to 130s, right? The good majority of it's right in the middle. So I'd say that's very believable. Just a few extremes either end, and a majority of the data in the same spot. I'm pretty sure that's right. I did it pretty quick, but I'm pretty sure I put the right number of things in there. Because for some reason I actually did make that instead of just copying it from the book. I don't know why. I guess. I don't know. Actually, it was funny. The book didn't miss one. I think maybe that's why I did it. I don't know. They missed this 9 right here on the 119. Unless I put an extra one of the two. Who knows? Any questions on stem and leaf? Pretty straightforward. Again, you can write them all down, but I think you get the idea. Obviously, you could just look at the recording, and there it is. That's why I'm saying I'm not too concerned if you sit there and write. This is kind of tedious at that point. Okay? I don't believe so. All right, a dot plot. Now, you can use it for this next one, and I'll just bring it to this page so that you can see it. All right? So a dot plot, I think you've done those before as well. And we'll just get that thing out of the way. A way of graphing, again, quantitative data, where each entry is plotted using a point above a horizontal axis. Okay? So I'll just bring that one here. So that you can see it. It makes doing this a lot faster because you've organized the data somehow. So basically you just go 78, right? So well, here's 80, so 78 is probably right about in there somewhere, right? So just above 78, put a dot. That's a dot plot. That's all it is. Then you just keep going. So we need to do 105. So 105, that's right there, right? Okay, so you put a dot. And 108, well, that's probably right about there, so you put a dot. 109, there's 3 of them. How do you do 3 of them then?
3 dots.
But just like what, right on top of each other, or what?
Yep.
Like that?
No.
And then that? And then that? Yep, that's how you do dot plots. Yep. And so that's the 109s. And again, I think you get the idea already. We're all very smart in here. I don't know that we need to do all the tedious work of doing all of them. But so we got 112 in there, right? How many of those we got? 3. 1, 2, 3. Okay. It's just another way of looking at the data. So 113, 114, 116, 17, 18, 19. So I did all those. Well, I got a little far off, but close enough. 121 twice, 122 3 times, 23, 24 twice, 26, 1, 2, 3, 4, 5, 1, 2, and again you get the idea. Okay. Again, that just kind of shows you how the data is distributed, and that's going to turn into be a very big word for us. How is it distributed? Okay. Okay. And again, you can finish that sometime if you're really bored in study hall or something. All right, a pie chart. Funny enough that just last week, another teacher was coming in talking about these and how to make them. It's a circle graph, obviously, that shows the relationships of parts to a whole. Obviously, the entire circle is the whole. Oh, well, it happens. Okay. I think, yeah, you were looking at graph. That's why we put the G in there, yeah. So it shows basically, again, the relationship of parts to a whole. And this is going to be a good test to see if you remember how to figure out relative frequency. Notice I've left that blank. But I have given you enough information to do the rest. Blank divided by blank. Yeah, that's very helpful. Actually, if you look at it this way, this sigma really ends up being n, because that's your sample size. And this is really, right here, this is frequency, isn't it? Yeah, this is basically f, right? And if you add, that's your sample size. So basically it is, relative frequency will always be, if you use those, f divided by n. And you should expect some decimal here, right? Because you've got 359 divided by that. So why don't you go ahead and do that first one, and then I'll show you the rest of the answers. I think I went to 3 decimal places. Yep. About, so you could say about 29.2%. Is that correct? So is the next one going to be bigger, smaller? Yeah, probably the biggest overall, correct? You want to take a guess? Not bad. Pretty close. And so there's your numbers. And I think it's obvious that that last one is by far the smallest, only 1.6%. You notice in your particular table, I've also given you a place to put the angle. That means what angle do I have to put in that circle to actually represent that 29.2%? And the very easiest way to do that, and that's why I told that other teacher to go with decimals for this particular spot instead of doing 3.6. Remember, that's what that teacher wanted to do. So we're going to take 0.292 and take it times the entire circle, which is 360 degrees. Because that would tell us what's 29.2% of the circle. And we'll just round to the nearest degree because we don't want to be sitting there trying to measure, tenths of a degrees. Yep, 105. Okay. And I'm sure that you can all handle doing that math for the rest of them, right? I mean, I don't think that's too overly complicated. And I think for once, we'll make you do, at least one by hand so that you get the idea. Some of these clear ones might be a little big for what you need. There are some paper ones in here if you want that. Okay, so decide which protractor it is you're going to want. Make sure you get the angles written down first. But yeah, I think maybe the paper ones for the size of circle you have on your paper might work out best. Okay, has everybody got down the angles? All right, so you start. I tried to put a center in there. How good did I do? That's not terrible. It's not terrible, right? And so what you kind of want to do is put a center in there that's relatively close. And you want to start with some kind of segment, some direction. It doesn't really matter. Obviously, you're going to use the bottom of your protractor as kind of a straight edge. And just get a radius in there somewhere. Okay, it doesn't matter where. I think most of you that have either had advanced math or whatnot are just going to do this one because that's just what you're so used to. Okay. So you've got that one in there. Let's back up. And line it up like that. And then what's our first one we got there? 105 degrees. Unfortunately, mine doesn't line up. But the beautiful thing is I can mark right on top of my protractor when you can't. So 105 is, do you agree right there? Because it starts on this line, and then you start adding up. Okay? So to agree that's 105 degrees. Right? So it goes like that. And so you just kind of mark it. Well, you know the conversion to radians. You can do that. And I'm just going to erase some of this stuff here. And again, I'm just going to use, because I don't have a straight edge necessarily at my disposal, so I'm just going to use this again. Just kind of connect it with that one. So it's pretty close, right? Pretty good right there. All right, and so what you're going to want to do, you can either keep drawing if you want, or go ahead and label what that is. And what is that, bus? Is that what it is? Okay, so give it some kind of bus. And then what you're going to want to do, whoops, get out of there. Go away. Well, whatever. It's just going to give you the answers. It's being ornery. And in the end, that's about what it should look like. Do you have to have the exact same slices in the exact same spot? No. Wherever you want to make those slices is fine. And probably the easiest way to make the next slice, is just turn your protractor, line it up. I think I'm going to make it a little smaller. All right. So then you just kind of line it up, put that right on the center. Ooh, that was pretty good. And what's our next one? Really for us is, 146 degrees if we do it the way we were doing it. So 146, whoop, right there. Okay. And you got, of course, you keep going, and that was air. Yep, air for that one. And as you can see, that's very similar if I just turn the circle a little bit. Whoops. It's about the same slice. See if I match it up. Pretty much the same slice. And again, I saw some of you kind of playing around with that on Excel the other day. It's quite simple to do a pie chart. And you just got to remember that it does kind of total things up for you. It does that sigma kind of for you. Yep. What does inter mean? Inter means between. That's why interstates go between states. Yeah. You were thinking intra. Intra-county. Yeah. Okay, so any questions on the pie graph? I think you've seen those before. No big deal, right? Paired data sets. I think you might have to flip over. Is that on the same page for you? Okay. Paired data. Well, you've dealt with paired data for quite some time. Same number of entries, and each entry in the first data set corresponds with an entry in the second. When you've graphed lines, you've had an x and a y, and you've always had the same number of x as you have y. You haven't just came up with another y value that you're not going to use, right? I mean, that's a paired data set. You get an ordered pairs, right? But basically, each entry has a corresponding second entry, I guess you could say. Or just use the idea of that ordered pair. Every x kind of has a y, especially when you do a line or some type of graph like that. And the best example of that is a scatter plot, which is why I have them on the same slide. All right, graph where ordered pairs are graphed as points on the coordinate plane. So basically, they take those paired data sets and they turn them into x and y, which is probably the best example of them anyways, and they put them on the coordinate plane. And we're going to look at scatter plots quite a bit. We're going to try and put that best fit line in there. You may have remember best fit line from Algebra 2. We're going to do I told you that's just kind of an approximation of that. We're going to do a much better job of that, and we're going to let the calculator do that. I'll show you how it's done, and we'll do the best fit line. We'll do a lot of talking about that. The graphing calculators are really good at doing that. And so here we go. Now notice I have put the x-axis and y-axis on there. I've altered my graph a little bit, given it some labels and stuff. You don't necessarily have that. But what I did on the x-axis, you may notice I made every 2 tick marks equal 1, and I made every 2 tick marks, well, I kind of just cheated. It would be a broken axis here on the y-axis. All right. But then I made like every 2 just 5 on this one. So the scales aren't the same, but we'll still get the idea of the scatter plot. And so as you can see, Over here, length of employment is in years, and that's basically your X values. And then the salary in dollars is your Y values. So you can just go ahead and graph those. Yeah, in thousands. Yep. Yeah, I probably should have put that on my axis. And I kind of cheated. Instead of graphing them every year, I just graphed them once. As soon as I find them, they're there. And now they'll just be there for me from now on. So why don't you take a second or two and do that. All right. So as we were working on this, somebody said, well, it looks as though there is definitely a trend. Obviously, the trend here is that as the length of employment gets larger, the salary also gets larger. Okay, that's would be, and basically you can see that there is a line that we could kind of throw in the middle there. Obviously, we would get more exact than that when we actually do these, but that line represents that data fairly well. Okay. And I think we all know that the slope of that line is positive or negative? Positive. So that'd be a positive correlation. Is it possible that some things could have a negative correlation? Yeah, there are things, you know. In general, you could say, well, no, that wouldn't work. Well, you could say after you get to age 30, your age and then your height. You do technically start getting shorter. Spine compresses, right? And so you get a little bit shorter. Okay. And we only have one more definition, time series. Data set that is composed of entries taken in regular intervals over a period of time. Of course, not O time, of time. So maybe, you know, every 2 seconds, or maybe it's every 10 years, or who knows. But it is a regular interval. A lot of times that'd be years, whenever you're given something like this. So say rate over a 10-year period or something like that. Yeah, O time.